Welcome, everyone, to the new season of Dots. We have several exciting sessions planned for you. This is the first one. The other ones will be posted on our website shortly. We start today with Harsha Nagarajan, who is part of Los Alamos National Laboratory in the Theoretical Division. And he received his PhD in mechanical engineering from Texas A&M in College Station in the area of controls and optimization. He's currently a staff scientist, and it's the Applied Mathematics and Plasma Physics Group, T-5, in Los Alamos. His research interests include developing theory and algorithms for solving discrete, stochastic, and non-convex optimization problems applied to large-scale networks in energy infrastructure and unmanned autonomous systems. So please, Harsha, you have the floor. 25 minutes to 30 minutes. We look forward to your talk. And by the way, for everyone who is joining, if this is your first time, we usually stick around afterwards, after both talks in breakout rooms. So please, if you have any questions, you can either ask them throughout, which is totally fine, or you can save them for the breakout rooms afterwards.
Very cool. Thanks a lot. Thanks for the introduction. And yeah, today I'll be talking about learning to accelerate partitioning-based algorithms for the global optimization of non-convex programs. And this is a joint work with my collaborators, Rohit and Deep, both from LANL. And I would say most of the lead work was taken by Rohit. And here is the paper, which we just updated on arXiv, and here's the link for that paper. Most of the details what I'll be presenting today will be present either from this paper or it could be from one of our previous papers, but this is the main, which has the core of the work. Great. So the outline of this talk is I'll give a brief introduction and motivation to be able to apply, machine learning as a tool for solving non-convex optimization problems, and why do we really care about it. And then I'll present an overview of an partitioning-based global optimization algorithm. And here we are looking at deriving MIP-based formulations, an iterative algorithm, which is based on the piecewise polyhedral formulations. And I'll give a brief overview of these formulations and how sensitive are these formulations or this MIP relaxation method to the type of partitions we choose. And then we'll propose a new or the novel strong partitioning policy and use this as an expert policy and to be able to imitate this using machine learning, using an approximation. And then finally, I'll present a few numerical results on a family of QCQPs, non-convex QCQPs, and then I'll conclude the presentation with the future directions. As we know, non-convex problems or non-convex programs appear in multiple applications. Here is the version of the deterministic problem which we are interested in. Here we are looking at minimizing a function f of x subject to constraints, which could be both equality and inequality constraints with variables which are in the real space. For our talk's purpose, we are only assuming the problems which have only continuous variables. At this point, we are looking at generalizing this to min-LP version of the problem, but for now, we'll be looking at the continuous nonlinear programs. So, and we know that these kind of problems appear in numerous applications. Particularly in the energy infrastructure problems, like in power grid optimization and gas network optimization, which are kind of the two applications which we are heavily invested in here at LANL. But we also are very interested in looking at other problems where this kind of a structure appears, like in the pooling problem, which is a very well-studied problem from the non-convex optimization perspective, and also the molecular structure completion problem in biology. So there are numerous of these applications where these such deterministic non-convex optimization problems appear. So in particular, looking at the motivation to be able to apply machine learning, we were heavily motivated from this application of the power grid optimization problem. Here, I'll certainly not bore you all with too much of this application, but I'll quickly give an overview, and then we'll get into the details of the formulations and algorithms. So as we can see here, for a given particular power grid on the right side of this figure, what you see here is basically a typical day's load profile across multiple days and across multiple years for the same grid. As we can see that across multiple years, the load profiles are not changing drastically, except for the year in 2020, where around March, when the COVID hit, of course, the world saw a sudden decrease in the peak demand. But other than that, as you can see that the load profiles has a certain structure and they follow that pretty much every year. Right. So there is certainly that structure, but more importantly, power grid operators, which are these, the independent system operators, are looking at solving large set of such non-convex problems with varying problem parameters. And here, by varying problem parameters, what we mean is, given a grid which has a constant topology, most typically we assume that the topology of the grid doesn't change across time periods, but given this grid, which has a same topology, what really changes across the time period, as you can see in this figure, is basically the loads and potentially renewable generation, etc. And this is exactly where we are looking at, when the semantics of the problem remain a constant, is there a way to apply machine learning and exploit this distribution-specific structure to be able to construct better heuristic decisions via imitation of certain useful policies, so to speak. All right. So with this, let's look at the kind of architecture we are interested in. So given a distribution of non-convex instances, by distribution, what we mean is, given a set of non-convex instances which come from a particular family, we have this training set of instances which are, equivalent to the historic load profiles of a power grid, what we saw in the previous slide. And for each of these training instances, we could learn, hopefully, the optimal algorithmic parameters, or what we call as also the heuristic decisions, which are part of a global optimization algorithm. And these, and based on this training, these parameters will get tuned within the global optimization solver. And once we have the new load profiles or the testing instances which come in real time, we should be able to hopefully solve these testing instances using this global optimizer, which is already now tuned based on all the training we have done for the algorithmic parameters. So why do we really care about is because it should hopefully lead to faster runtimes. And most importantly, there is not going to be any compromise on the optimality guarantees, because we are only looking at tuning the algorithmic parameters to be able to make the optimizer best for this family of non-convex instances, instead of directly predicting the solutions of the problem, where there are certainly a lot of advantages, but then that has its own issues with respect to feasibility, etc. In our work in this presentation, I'll be only looking at accelerating the solver where the global optimality guarantees still hold true. Okay. So of course, this kind of structure and exploiting this kind of distribution-specific structure is not really new. This has been certainly exploited quite a bit in the literature of mixed integer linear programs. There are already many papers which do that, but I will not get into that detail. But since our talk is on non-convex problems, I was just making the list of all the papers which have looked at non-convex optimization and learning intersection, right? So here, to the best of our knowledge, we could find probably this is the most comprehensive list of papers where learning has been applied for non-convex problems. So as you can see, there are really not many papers. I'll not get into the details. If you really are interested in the details, I would suggest to look at the archive paper, what we have uploaded. But if you look at, for example, this particular paper, which is kind of the nearest, I would say, here they are looking at solving non-convex optimization quadratically constrained quadratic programs. And here a trained neural network is being used to be able to out-approximate a sum-of-net constraint using cutting planes. And the neural network basically predicts the best cutting planes from the either the optimality-based perspective or a feasibility-based perspective, which could out-approximate these sum-of-net constraints to tighten the lower bounds of the problem. So, and of course, there are also other methods where learning has been applied for spatial branching, where the focus is more on the algorithmic selection approach and trying to enhance, RLT relaxations for polynomial optimization problems with conic constraints, where since RLT relaxations can become quite expensive very quickly, can we use learning to be able to choose the right amount of RLT relaxations to be applied while branching for attaining global optimum solutions. And mostly in our recent work, we kind of looked at an application of the power grid optimization, which is the AC optimal power flow problem, where we were looking at applying machine learning approaches. But here we are looking at primarily from bound propagation and bound tightening algorithms. But to summarize from this literature, there really aren't too many papers where which focuses on some sort of a full global optimization algorithm which guarantees optimalities, and also more on this kind of sequential MIP relaxation approach based on partitioning methods, which has kind of picked up quite a bit in the global optimization literature of it. So that's what will be the focus of this talk. Okay, I'll quickly digress on the partitioning-based global optimization method. I'll give a quick background before we get into the actual details. And here, before I progress, if there is any question, I'll be happy to take. Else, I'll progress with the partitioning-based algorithms. All right, I'll probably head on.
I think very clear so far. Yeah.
Cool. Thank you. All right. So a quick overview of global optimization. Certainly, this overview is going to be at a very high level panoramic view, but then I'll of course, I'll not get into the too many nitty-gritty details of the algorithm, but here is kind of the global picture of it. So let's take a one-dimensional function within this domain, the fixed domain of -2.5 to 2.5. And for this, the goal is to find the global optimum for this problem. And for that purpose, the two primary ingredients of being able to obtain the global optimum is to be able to obtain a good upper bound, which is usually done using local solvers, which are based on heuristics, and to be able to obtain a good lower bound. And this lower bound is usually obtained by applying convex relaxation. So as you can see, the tighter this green region is, the tighter the lower bound for the problem. And when we evaluate this optimality gap between this upper bound and the best known lower bound, and if this gap is within a certain prescribed limit, then we have the global optimum solution. Else, we need to do something more. So for that purpose, we have to branch on that variable. Since this is a unidimensional function, we only are looking at one particular variable. And here, in this case, let's assume that we branch at the origin. And if we branch here, so we basically have two separate regions where we apply independent convex relaxations. And the advantage of applying these independent convex relaxations is that you end up getting tighter relaxations when you have tighter bounds on the variables, and this process can be iteratively continued. But how do we get rid of these regions is basically looking at certain best known lower bound and the upper bounds. And in this case, as we can see that the best known lower bound on the left region is already greater than the best upper bound of the right-hand side region. And with this, we can safely prune this left region, and we can continue spatially partitioning on the right region. So, and this algorithm kind of continues, very similar to the way it happens in mixed integer linear programs, but here basically we are generalizing with nonlinear programs, right? So with this, as I mentioned, there are different steps which have to be taken into account, which is either doing local solving through heuristics or in building convex relaxations and being able to solve these relaxations. And how do I apply pruning schemes, and then the partitioning algorithm. So in this talk, we will be kind of mainly focusing on just this particular aspect of the algorithm, which is on the partitioning algorithm, and how can that affect the convergence of these these partitioning methods, and to obtain the global solution through using that. So for that, we look at, as I mentioned, there are multiple methods with which global optimization can be applied. One is using the spatial branch and bound approach, but the other one which has picked up more recently is the MIP relaxation-based approach, because of the recent development of all the MIP solvers, like the commercial solvers like Gurobi Cplex. They do really well on MIP. So let us exploit that fact and develop, instead of doing spatial branch and bound, instead let us develop good MIP relaxations for the non-convex problem and apply this in a sequential procedure. So for this purpose, to be able to derive a MIP, we have to introduce two binary variables to be able to represent these individual regions, and to be able to have one of these regions active in the set. So for that, we invoke the theory of degenerative programming. And here, the idea of degenerative programming, what we are invoking is basically quite straightforward, that when one of these regions is active, we have basically those particular relaxations, convex relaxation, that region's convex relaxation active. And then all we are really interested in looking at is to derive the convex hull of the disjunctive union of these two sets. Okay, so if we are looking at this convex hull of the disjunctive union, of course, why do we care about such a disjunctive programming approach? It is well known that the LP relaxations are usually tighter than the big N constraints, and it can be very effective to be able to write a good MIP and to be able to solve it fairly fast. But of course, the challenging part is, how do I derive such compact algebraic characterizations and so on and so forth, especially for non-convex functions and its relaxations. So let us look, and that's basically is what we will be looking at in the next few slides. So to make things a bit more concrete, given this problem, we are looking at functions, the f, c, and h, which can be some of individual multilinear terms of the form phi of x. So now we will be looking at presenting the theory and the theory for deriving the piecewise polyhedral relaxations for the graph of this function phi of x, where the graph of the function is given by cap x as defined in the bottom. So here we are looking at for the just the explanatory purposes, we are looking at only the bilinear terms, but the theory extends to multilinear terms as we have also in the paper. But I'll just present the formulations, what we derive for just the bilinear term in this case. So as we know, given a bilinear function, we know that this is a non-convex function. And for this non-convex function, the convex hull can be obtained by applying 4 facets. And this is the hyperplane representation. And those 4 constraints are also what are the well-known McCormick relaxations or the McCormick constraints. And we can apply this relaxation and we basically get the tightest relaxation for a given individual bilinear term. But we can also look at it from the slightly different perspective, which is looking at the vertex representation or also the extreme point representation. So here we enumerate all the extreme points and we derive this convex hull, which is just the convex combination of these extreme points, where it comes at a cost of adding these additional non-negative multiplier variables. And it still captures exactly the same feasible region, what the hyperplane representation does. But the advantage of doing this lambda formulation is that it could be easily generalized for any multilinear terms, which is not possible trivially by applying this kind of the hyperplane representation method, because applying Fourier-Motzkin method and being able to project out all these lambda variables and to derive these facets is not really trivial. So instead, what we are looking at is using this kind of what we call as the lambda formulation. And this lambda formulation is capturing the convex hull of a given multilinear term. And of course, it generalizes to any number of multilinear variables, but comes at the cost of having exponential number of these lambda variables because of the nature of the number of extreme points, which are exponential. So we have a slight fix for that. I'll get to that later. But before that, to derive this piecewise polyhedral relaxation, let's look at the univariate partitioning. So given this bilinear term, let's look at just partitioning on one axis of this bilinear product. So in this case, let's look at just the one x2 as the partitioning variable. So here, as we can see that we apply, when we apply these piecewise polytopes or piecewise McCormick envelopes or what we call as piecewise lambda polytopes. So they give you the tightest relaxation. And we can also represent that in the form of a grid, where the shared extreme points of this polytope are also represented by the gray extreme points, and those are the extreme points which can also be represented in the grid form on the right figure here. Okay, so this is assuming that a single variable is partitioned, but let us say that we want to partition, do bivariate partitioning, for example, which is both the variables. It will be not possible to plot this function as simple, so we basically end up using this kind of a grid representation. And here we assume that one of these binary variables is active in each of these axes. Okay, so this is assuming that both the variables are partitioned in this case. And with that, there is basically one of the formulations, which is kind of the well-known formulation, which we adopted from this particular paper, and we generalized that for the relaxation formulation. Here, this was done for approximating a nonlinear one-dimensional function, but then we kind of took that and we generalized that for higher dimensional functions. But this is the more popularly known as the convex combination formulation, what we call as the PPR1. One thing to notice this formulation is that the constraints are fairly sparse in the lambda variables, which represents the extreme points, which are basically the shared points across the polytopes of the relaxations. But we also derive this facet formulation, which leads to dense constraints. But we call this facet formulation because it has some nice theoretical properties. And looking at the polyhedral properties of this, so what we call as the facet formulation is also something called as a locally ideal formulation, and this captures the convex hull in the original space of variables, which is theoretically a better formulation. But looking at the other formulation, what we presented as a convex combination formulation satisfies a slightly weaker condition, which is also known as a locally short formulation. But here, it does not necessarily capture the convex hull in the original space of variables. But as as always, many times theory doesn't match with practice. The PPR1 or the locally short formulation, which satisfies the weaker condition, seems to perform much better than the locally ideal formulation, and so we basically use this as a reference for every partitioning algorithm we basically implement from now on. So As I also alluded briefly earlier, that the number of extreme points could be exponential. So from that perspective, we basically are looking at applying these recursive PPR formulations over a multilinear term. And we also derive certain properties, and we compare the performance of these with respect to the locally ideal formulation in this paper. If anybody's interested, I would suggest to look at this paper, but we will be sticking to PPR1 formulation for this testing. But with this, now that we have derived the PPR formulation, now let us look at the actual choice of these partitioning points, which is the primary focus of this talk. And here, as we see here, we have looked at uniformly partitioning this domain and locating these partitioning points in this grid form. However, we could certainly, perturb these partitioning points, and we can still derive these PPR formulations. But there are a lot of heuristic choices which need to be done. For example, when we have a certain lower bounding point, can we basically bisect at that point, or can we do some sort of an adaptive partitioning strategy? So there are multiple choices which need to be taken, but the question is which one does the best, right? So recently we had a work where we looked at having this kind of an adaptive partitioning strategy. As we can see for this one-dimensional function, what we started with initially, the idea is to look at the feasible point and then add an adaptive partition around this feasible region, which is guided by, it could be either with the best known local solution or could be based on the best known lower bounding solution. And this basically, the whole idea of this, this algorithm was to see if can we basically adaptively add partitions without making the MIPS too expensive, because as we add more and more partitions, we get tighter lower bounds, but they become harder MIPS to solve. So in this paper, we kind of observed that this algorithm behaves pretty well. But we are looking at something more interesting, which is how do the sensitivity of the scaling of these size of these added partitions behave with respect to this algorithm. So as you can see in this picture, as we change the size of this active partition, or whatever as the adaptive partition, which we call, as we change the size of this partition, clearly for a set of 3 random QCQP, non-convex QCQP instances, the runtimes are quite varied. And especially, for example, if we choose the medium-sized partition for that particular instance, which is QCQP1, we get a speed up to 7.2x. So from this, clearly, there is a lot of sensitivity based on the choice of these partitioning points and how we could speed up this algorithm based on this choice of these partitions. So now the question is, can we choose optimal partitioning points or better partitioning points for the factor convergence of this algorithm? So for this is where we basically propose the whole idea of the strong partitioning and its ML approximation. I know I don't have too much time left, I think, but if there is any question, I can certainly take at this point before I proceed to the actual part of the presentation.
You still have, let's say, 5-7 minutes.
Okay. Yeah, I think I should be able to cover that now. Okay, so the idea of strong partitioning, or what we call as the SP policy, is to be able to choose these partitioning points to be able to maximize the lower bound of the PPR, or the piecewise polyhedral relaxation formulation, what we obtain. So for this, we basically solve a max-min problem. So the idea is to choose a set of partitioning points and solve this parameterized value function, which is parameterized by the set of partitioning points, where the value function is evaluated based on minimizing this non-convex problem with the piecewise polyhedral relaxation parameterized by P. So the idea is to basically solve this max-min problem, which provides the set of partitioning points P star, which are the optimal partitioning points for the given QCQP or the non-convex problem, which we are interested in. So at this point, we are looking at applying this SP policy just at the first iteration of this lower bounding partitioning algorithm, which I mentioned earlier, because the choice of those initial partitions can be quite sensitive to the convergence of the algorithm, and also it can become a bit non-trivial to be able to apply this algorithm, this kind of a policy at subsequent iterations. But the idea is that even though we apply this at the first iteration, the subsequent iterations are still guaranteed to converge to the near global optimum solutions with a strong partitioning policy. So this is, I would say that this is also very much in the lines of the strong branching, where the branching is chosen to be able to maximize the minimum lower bound while branching down a variable in the mixed integer program, linear program. But here the challenge comes from the choice of this partitioning points over this infinite region of the within the bounds of the variables. And that's where the challenge comes into the picture. So in that spirit, basically, this maximum SP problem can be formulated as a generalized semi-infinite program. But of course, solving this to global optimality can be just as hard as solving the original non-convex problem. So for this, we basically design a local optimization method to be able to solve this SP to obtain this P star that yields hopefully a tight lower bound to this value function BPPR, parameterized by this P star. So for this purpose, we basically use the generalized gradients of the value function VPPR to be able to compute the sensitivities. And based on the sensitivities, to be able to compute the sensitivities, we depend on this useful structure that the piecewise McCormick or the piecewise lambda formulation, what we formulated earlier, also has this nice useful structure, which is piecewise linear, and they are still continuous functions. And for this purpose, we basically exploit this proximal bundle solver, what is the MPBNGC solver in this reference, which is typically used for non-smooth, non-convex optimization. And this is how we basically locally solve this SP problem. Once this SP problem is solved to local optimality, so what do we do next? So for this, we basically generate this family of random non-convex instances, which are parameterized by the parameter theta. And as we saw earlier, we classify these instances into separate set of training instances and the testing instances. And for the training instances, we basically solve the strong partitioning problem, which is the max-min problem, to local optimality to be able to obtain these optimal partitioning points, is what we call them. And once we learn to partition, we basically train an ML model which basically maps the problem instance to the output of the partitioning points. And once we have a testing instance, the inputs, what we are looking at to be to feed into this trained ML model is basically of course, the instance, which is parameterized by data test, and the convex relaxation solution, which are easy to evaluate again, which is the X lower bar, and the local feasible solution, which is also hopefully too easily to evaluate and obtain that as an upper bound. And since these are easy to evaluate inputs, we have these as right now the inputs for this trained ML model, which predicts the optimal partitioning points for the global optimization algorithm. And the algorithm is basically going to use these predicted partitioning points just for the first iteration, and then performs the usual regular adaptive partitioning strategy for the remaining iterations. Okay, so this is how we try to imitate the SP policy. And of course, not surprisingly, the step of the training step is not very cheap, but that is where we basically are trying to work on how do we improve this training time for the problem, for example. So let's look at quickly the numerical results based on these ideas. So we use, the usual stuff like MIP relaxation solver is the Groby, the non-convex solver is IPOP, but mainly we use Alpine as our global optimization algorithm, which is the partitioning-based global optimization algorithm. That's the basis what we are going to be testing on. And then we implement these this learned models to it. Okay, so we look at a family of random QCQPs. Here is the details. I'll not get into the details, but we test on one random family of QCQPs and also a random family of pooling QCQP problems, which are fairly larger problems. And then we basically do training samples of 1,000 training samples with varying parameters theta. And we also perform a 10-fold cross-validation for predictions. And for the trained ML model, we basically use the scikit-learn's AdaBoost regressor to train the regression trees, but we are not using anything very fancy at this point, just a very simple ML model. So here is the solution profiles, basically. As we can see, as we increase the size of the problem, of course, the higher is the better in this figure, and the default represents the Alpine's default runtimes, and then SP2 basically represents the strong partitioning when we add just 2 partitioning points at the first iteration, and the ML2 represents the imitation of this SP2. As we can see that at the lower sizes of the problem, the ML2 quite well approximates the problem of the exploit policy with this huge runtime gain. But as we increase the size of the problem, we certainly are, the ML model is not able to approximate the strong partitioning as well, but then certainly the strong partitioning method does really well in trying to close the optimality gaps fairly fast. And also the amount of optimality gaps closed in the first iteration of the expert policy and its approximation ML can be seen in these figures, where we are able to close a huge optimality gap in just the first iteration by choosing the right partitioning points for the MIP which we solve. So when we perform this kind of an over average tenfold testing, we basically.
So Harsha, just to let you know, about 1 more minute left.
Okay, I'll wrap up with this. So basically, I'm going to wrap up saying that there is a huge speed up which we obtain by choosing these different types of partitioning points, which we get up to 49x to 60x speed up by using these using this expert policy and ML approximation. And we also tested on the pooling problem, where it is interesting to see that across the 1,000 instances, around 45% of instances we could close the optimality gap just in the first iteration by using this expert policy, but could not be done by just the regular default Alpine. And with the runtimes with respect to Baron, we could see that there was a huge speed up because we wanted to just observe how non-trivial are these instances, and they are indeed non-trivial when we compare to the state-of-the-art solver, Baron optimization solver. Anyway, so I would like to basically conclude with this saying that this is pretty much, I would say, kind of to the best of our knowledge, the first demonstration of learning for global optimization based on partitioning algorithms for non-convex programs. Certainly, the strong partitioning policy provides an excellent benchmark for the ML to be able to accelerate partitioning algorithms. And we saw a huge speed up by using these kind of learning methods when implemented in the solver Alpine. So there are many future directions we are looking at. In short, I would like to generalize. I would like to say that generalization of these ML models, especially based on graph neural networks, is quite challenging because currently the ML models what we have, if we have trained on a particular number of variables, it is very difficult to generalize that to a larger problem, so to speak, so without performance degradation. So that is something which we are looking at, and also potentially to see if we can, learn effective decision policies autonomously using reinforcement learning type methods. With this, I would also like to acknowledge some of the contributors for Alpine and the student who worked on this work, and I will thank you and take any questions now. I'm sorry I was a little bit late, but yeah.
That's totally fine. Thank you so much. I guess in the interest of time, let's leave most of the questions for Harsha to the breakout room that will happen in about half an hour after Kevin's talk. But please do save your questions and stick around for that if you're able to. So let's thank Harsha one more time, and then Kevin, we'll let you give us a moment to get set up.